Okay, so it is my great pleasure to introduce Leonid Gurvits, who's going to be giving the Colloquium today. He comes from City College, New York, in New York City. Leonid has done a lot of great work, a lot of very prescient work, and at least some of that great work fits into sort of log, concave, and hyperbolic polynomials. But I'm very excited about his talk today because he's going to be talking about something from his pre-hyperbolic days. He's going to be talking about combinatorial and complexity theoretic aspects of stabilities and controllabilities of linear switch systems. So, Leonid.
Okay, thanks a lot. And it's always honestly, it's always a great pleasure and fun to visit University of Waterloo. Yeah. And in general, I like Canada and Waterloo especially. So, a little story. Lately, I kind of tried to give, because I'm not looking for a job already. Like lately, I'm trying to give kind of personal talks, which people forget. That science discoveries so far made by human beings, and human beings, they have problems. They could be unemployed, which I was for quite a while in my life and still doing research. You can go to some personal problems, But anyways, I think it's pretty important part of, and unfortunately it's missed when people, okay. But now at my age and status, I have a luxury to be kind of cool in that way. Okay, so what I will be talking today is not new. Okay, even some of it even was published, but some of it was published in reasonably major journals, some of it in conferences. So, but the two things which I will be talking today is kind of interesting story. They were around 2005, okay? And I started to think about this kind of hyperbolic generalization of van der Waerden, okay, in 2004, okay, and I had like no idea how to prove it, and I actually, and I'm very grateful to all those people whom I asked for advice and who had no advice to give to me. I'm so grateful to them. Okay, and so, okay, and so what happened, one of the results which I will be presenting, it's about some strange necessary and sufficient condition for existence of Hadamard matrices, which comes from control theory. I done with my great friend and colleague, Samorodnitsky, so he was my co-author when we did this first paper which led to all this stuff about mixed discriminants. And actually, I was at that time in Los Alamos, and there was this very short period in my life when I was awash in money. I couldn't buy. It was a very short period in my life. Okay, and so essentially, I had money to invite, and I thought we would talk about this hyperbolic stuff. And nothing, there were no ideas. And again, I'm very grateful to Alex that we had no ideas. And we started to think about some things we could still do, and then I was still thinking about those things like joint spectral radius, which I will define. And that work came from that. The another part which I will be talking about, which has some kind of a little quantum probably flavor, so I also, because I had no idea how to prove that hyperbolic conjecture, and I had money to invite people, so I invited a few graduate students to do simulations to see, the numbers were okay. And it happened to me that before they came, I already proved without any simulation. And it pretty much And they were not on that level to talk about deep generalization of that stuff. And one of them was, I think the funny thing is that there were like 3 of them. Almost all of them now in kind of AI stuff. 2 of them in AI, but one of them, which was a quarter of that, he's still, he's still a scientist, but anyway. And we started to think about this problem about, okay, so the cool thing about the second part about this kind of NP hardness of checking or something, it's probably, again, as far as I know, it's maybe, again, I don't know about everything, certainly. I think it's one of the very few results of NP hardness which uses measure theory, Lebesgue integrals and all that stuff. So again, it's impossible without, okay. So the first part of the talk, I will give you a little tutorial, what is the joint spectrum radius and all the jazz, okay? So what do I have? The object.
Hey, Leonid, do you think you could start here?
He is fine?
After this arrow, the squiggle and the arrow?
He is fine?
In between, yeah.
Yeah, okay. So I have a set. So they either matrices in n-dimensional complex or could be real. I will point when they need to be real. Or actually even operators in some Banach spaces. So many things they work in Banach spaces. And here's the definition. By the way, who knows what is joint spectrum radius? Okay, you also know, good. So here's the definition. I will give a straight definition. So again, A omega is a word in alphabet 1K, and A omega is usual. So if omega is the word, it's just the product. So what do? You take all possible product of lengths n, and you compute, you take any norm, because everything is equivalent. In finite dimensional case, in infinite dimensional case, you will need to take the norm which is. And this is induced norm, which comes from that. So go through all possible products, compute their norms, take maximum of those, and normalize, take 1 over the length root, okay? And you can see that if it's one matrix, that it's actually a theorem about spectrum radius. Okay. So here we take just this theorem, and we turn it into definition. Okay? And it's happened to be, not surprisingly.
Sorry, in the first column, A is like one of the A1 to AK? Or
Huh?
what is
Yeah, I have K matrices.
And so you're taking the maximum of K?
No, I take maximum over all their products of length L. This is the length of the word. Okay? And again, this is just a kind of non-commutative generalization of standard formula for spectrum radius, okay? And it's happened to be, again, not really hard to prove. actually pretty simple. So essentially, what do? You go through all possible norms in CN, compute those induced norms, take maximum, okay, and take infimum over all possible. So again, for one matrix, what it says that spectral radius can be approximated by induced operator norm, okay? Okay. So this is one thing. And actually, there is another definition here.
Is there any normalization condition on the norm?
What?
Is there any normalization condition on the norm?
No, because this is induced operator norm. So,
I see. As an operator.
or, by the way, you can take any multiplicative, submultiplicative norm on matrices. It also would work. Okay? And there is one more definition. So what is the definition? You take all products of, okay, compute just standard spectrum radius, and normalize it, okay, and take sup over all possible products. And of course, this thing is supposed to be, because spectrum radius is less or equal than any induced norm, but they happen to be equal, okay? So here's a little personal story. I started to think about those things in late when I was still in Soviet Union, late 1980s in Ukraine, okay? And so immigration, and I proved, actually I kind of proved this thing, but it was not published, okay? I come to America and no job. I'm just, I was unemployed, okay? And it's another story how I got the job. But anyway, it was not like this normal story. Like those, this famous Russian, mathematicians, they come to Canada, job is waiting for him, car is waiting for him, maybe even wife is waiting for him. I don't know, like everything like that. No. I don't know. It was not like that. So anyways, when I kind of got settled a little bit, and I was supposed to work, I was working in robotics research lab. So I was actually doing something which is called non-holonomic control, which is about, actually it's related to quantum computing. Actually it's application of Lie algebras, okay? And I got a little, and now I started to look at the literature, and I see, this stuff about those product of matrices is so popular in America. Why? Who knows why? It's like interesting, those waves of what are hot topics. At that time, hot topic was wavelets. It was the Ingrid Dubush and Lagarius, and they had this paper about these two-scale equations, how to build wavelets. And they built certain functions, and the smoothness of those functions is due to things like this, okay? And it happened to be that, and this result was actually proved. The paper was published in 92, Berger work. But actually, my proof was very different, that one which I had in Soviet Union. I actually will kind of sketch it, okay? So, and it's pretty simple and neat. So really, what you want to prove? You want to prove this generalization of standard result. So if you have spectral radius equal 1, okay, it does not mean that those powers are bounded. Okay? They might have polynomial growth, okay? But what it really means is this, that matrix can be partitioned into blocks and it will be this block upper triangular structure, and each those block, if you will take powers, will be a bounded set of. Okay. So what do you want? You want to have, and after that everything follows. You want to have a similar result for this guy. So you want to have that if this is for many matrices, actually it works for compacts. So if you have this guy, if this guy is equal 1, then all those matrices can be, there is common partition of the space such that all those matrices will have this upper diagonal structure, and each diagonal block will give you a bounded set. And after that, everything. Okay? And how you prove it? And you prove it actually by this trick, which I kind of knew from my university years, okay? So essentially, what do you need? You want to have this thing. So if you know that this is equal 1, you want to prove that there exist non-zero x This is what you want to prove. And now you just collect all of them, and they will give you a linear space, because it's a linear condition here. Okay. So now suppose that for any non-zero x, even like this, they exist word.
Supremum above is over words?
Yes. So again, you generate this entire semigroup, apply to this, and you want to have the bounded set of vectors, okay? And suppose that it's not even, you assume that it's just for any x that exists, let's say 2. It can be any number greater than 1. So again, if it's not true, of course, it can be any number here, okay? So now what do? You take unit sphere, and you cover by balls. You take x. There will be open ball, which covers the things, such that, in some word, such that on this will be greater, let's say, than 1.5. Okay? And now compactness starts to play. So we cover by balls this compact, which is unit sphere. So it will be finite. Okay? So I will give this finite set of words. Okay? And now I can construct. So I will start with x, which covered by this word. I will apply this guy. So now it will be another dead ball. So I will apply. Okay? And after application of each guy, so I will have, if I do it like m times, it will be greater than. Okay? And this will contradict to this guy, because that limit will be greater than 1. That's it. And after that, things are extremely simple. And after that, things are, who knows, there is this famous result in combinatorics, Koenig theorem about infinite path in trees. So if you have infinite tree, okay, yeah. Who knows how to prove it? Actually, it's kind of dependent on axiom of choice. But the point is, there is, of course, and there are many, there are other examples how to get from to Ramsey theory. It's also how to get from infinite Ramsey theory, finite Ramsey, just existence, not exact constant. So all those things can be proved by compactness. So for instance, in terms, for the Koenig, it just essentially compactness of finite sets. Okay, this is how you can build that. And I strongly encourage you to think how you can prove by standard compactness argument. It's kind of trivial diagonalization argument. And those things, they start to play here. Okay, so, and now I will give you example to give the feel what is going on. To get some connection to your glorious department. Let's consider this case with those matrices of rank 1. Okay? And I want to compute on this. Like rank 1 usually simple, separable. Okay? So how you compute the things here, and that thing, which is based on spectral radius, actually can be computed in a very simple way. And there is effective algorithm. So you just build this matrix. So it will be K by K matrix. Okay? So what are product quantities which are, quantities which involves product and they can be efficiently computed, non-trivial. Who can tell me? Huh? No, what is that? So you have the same matrix, let's say with non-negative entries. What kind of quantity which depends on the matrix, which involves products, and non-trivial, Determinant, what else? But for non-negative, it's, determinant is not good. Okay? There is this cool thing. You go through all cycles, take products, and normalize it. So take cycle. Cycle, I1 to I2, and eventually go back. Length, take absolute value. Of course, it will be absolute value for this man. Take 1 over length, okay? And compute maximum over all cycles. This is classical quantity, which can be computed in okay, the standard quantity is not product, but sum. Yeah. And it's one of those beautiful things which can be computed, okay? So this happened to be just by definition of spectral radius, the formula for this guy, okay? But you know that if, let's say, you have a positive matrix and mean of this negative matrix, a mean of all those average cycles is, say, less or equal than 1, or less or equal than D, that it can be scaled to matrix with all entries less or equal than D in absolute value. So again, if this thing is less or equal than D, then you can find out and it's a classical result. And in this case, you can prove that if you have this, that the joint spectral radius will be equal to the D. Okay. Okay, so this is, but the point is the proof of this general result is actually even simpler than this, okay? Okay, but this was just a short introduction to discrete stuff. I will also talk about continuous. Now like reasonably new stuff. Now let us introduce Euclidean joint radius. So what I will do, so essentially here I will go only to norms which are like this. I just will try to approximate that things by standard Euclidean norms. So why, I don't know, semi-definite programming, you can do these things, okay? So let's call this guy, so this is the definition. Actually, I will write in a kind of So what do? I do, this is the same as to say, is to go to row positive. Instead, what I do, I fix my matrices, I do similarity transformations, and I compute standard norm from L2 to L2. And I go to all those guys. It's the same as to approximate, as to compute maximum of all those Euclidean norms, okay? And of course, this guy will be because okay, now, but how much bigger? And you can tell me now how much bigger. So there are obvious bounds. Okay, there is a beautiful Fritz John. I actually met him. Funny thing is that I was at Courant when he was still there. I did not, at that time I just was not aware about many things. And, okay. So Fritz John, any norm can be approximated by Euclidean norm, by any norm. You can stick this ellipse that by factor root of n will, okay. So any norm in Rn can be approximated by Euclidean norm with, let's say, factor root of n. What about Cn? To say that any norm in Cn can be approximated by a factor of root n, it's not true. Because Cn is actually R to n. Yes, but if you put extra condition on the norm, for any complex number z, if you put this condition, then you can approximate by, okay, why is that? It's actually quite interesting, because when I'm writing that paper, because this Fritz John result, everybody knows that root of n factor, or in non-symmetric case, it's n factor. But there is another very important feature of that result, which is uniqueness of that minimum thing. So, and that uniqueness helps you in the following sense, that if you know that your object, that your norm, that ball has symmetries, that unique guy is supposed to have symmetries. the same, okay? And in this way, you can prove that. So what that will help you? So if you just apply standard, that result, so it will be just 2n by 2n matrix. But the point is that it's supposed to be symmetric to those transformations, and it will force that matrix to n by 2n to be actually n by n Hermitian matrix. So if you will write carefully things, and it's pretty simple. The another application of this invariance of uniqueness of the ball. So, and I remember that Scott Oranson was writing all those popularization papers. So, and what are unitary metrics in LP in LP norm when P is not 2? Okay, and it's a cute exercise. And there are not that many of them. Essentially, they are permutation matrices, if P is not equal to. They are permutation matrices times diagonal with plus minus ones. That's it. And how you prove it, this is how you prove it. You take, let's say, LP, and that optimal and say that minimal or maximal volume will be just standard Euclidean ball, okay? So now if you have a matrix which is isometry with respect to that guy, that ball of standard Euclidean supposed to be invariant for that guy, which means it's supposed to be unitary in the standard sense. And now you just play with it and you see this is the only possibility. So, yeah?
Sorry to go back a little bit. Is there a promise on the capital D?
No. Okay. This standard result. If you go through all cycles and normalize them, okay, and they are less or equal than D, small d, then you can find out positive matrix D and rescale it such that this will be okay. Yeah. Yeah. Okay. So now, okay. So yes.
Unitary for LP norm is what? A linear operator that preserves it?
Yes, preserve LP norm. Yeah. And again, the point is because of there are other proofs. They're messy, but the simple proof is this: use this minimal volume. Does not say that the question that you need to use that. Okay, but that gives you a really simple proof. And actually, it's written in my paper with Alex Samorodnitsky that how to do that, okay? Or maybe not. No, I think only complex case. Okay, so now about this. So then what we can say for sure, that Euclidean guy it's just that free John stuff, okay? Yeah, but this does not care about how many guys in the set S. So if set S is just one matrix, then we don't need root of n. Okay, who knows about this beautiful simple result? That if you have any matrix, okay, then its spectrum radius can be approximated by Euclidean norm. Okay? And how you do it, it's actually pretty simple. You take your matrix A, you divide by spectrum radius plus some epsilon to make spectrum radius less than 1. You can take any positive. So anyway, so what you do, you normalize your matrix to have spectrum radius less than 1, forcing powers to converge to 0 exponentially. Take here star, or in a real case it will be transpose. Take any positive definite matrix, and take P this will be some positive definite matrix. Okay? So, and it's very easy exercise. X is positive definite. And you can take any, for instance, identity. Will be very easy exercise to prove that this P, which is actually kind of solution of Lyapunov equation, but we don't need to say that that's it, and you multiply and you. So if you will take square roots, it will be okay. So, but now you can use this trick to do when you have not one matrix by K matrices. Okay? So how you use this trick when you have K matrices? It's not good. So what is the attempt? What you need to do? You will take just this. To all possible, let's say, greater, including empty, it would be like just that guy, okay? But you want this guy to converge, okay? So it's happened to be that in order for this guy to converge, the joint spectrum radius, and it's pretty much like what was there. Why? Because again, I will count how many words of length L, it would be K to the power L, and I will do some simple, okay? So this gives you this. Where is that, my bound? And we get this formula, this inequality. Oh, let's write it like this. Okay, so not surprisingly, as most of simple results, this thing was rediscovered by so many people, including myself. Okay, I actually knew it actually I had the paper in 95. It was published, but it was submitted like in 91, which already has something very close to this. But if I'm not mistaken, the first published was 96, Ando, that famous Japanese analyst, and Shin. But again, I stress that most of simple results, they've been rediscovered many, many times, and by many, many people. And somehow there are not that many proofs of Fermat theorem. Just one, okay? But simple things, they have millions of proofs, okay? Anyways. So now question is, how tight is this bound? What is your guess? Okay. It is tight in complex case. And I will explain in a second. In real case, it is not. Okay? So for instance, that number, that function of nn, when n matrices, okay, would be supposed to be equal n if it's tight. If and only if there exists n by n real Hadamard matrix. So this is the result, okay? And moreover, what are the extreme? And you can describe in both cases, if real or in complex, if they exist. So what are the extreme sets? This is another cheer for Hadamard matrices. But anyways, so what are extreme sets? They're up to similarity. They're rank 1 matrices. Okay. This is standard basis, up to similarity, meaning in general, you should do similarity transformation. Okay, which is expected because of that. So, but in this, so again, those are the basis vectors. And now what about those guys? So this matrix, if you stack those columns in one matrix, it's supposed to be Hadamard. And entries, of course, in absolute value 1. In the complex case, we have those guys. Okay. So this is kind of, again, if you're into the stuff, it's a kind of cool exercise. So prove that for those guys, okay, there is no Euclidean norm such that they all have norm strictly less than root of n. It's simple, but it's kind of cute, okay? And so this is the result. And so what do in the real case you can ask, but what's supposed to be k? What's supposed to be k to get this root of n, that factor? Okay, so you can do. Okay, in other things which you can use in this context, so it won't be root of n, but you can express that factor in the real case in terms of the, you go through all possible plus minus 1 matrices, and you're asking for the largest, smallest singular value. And you can express bound in terms of that guy. Okay? So, and the proof of this, they're tricky, but again, it's Gurvits, Samorodnitsky. The conference called CDC 2005. So it was in proceedings of that conference. Okay? decision and control. Actually, it's interesting thing that my background before I came to America, okay, it's all, again, it also kind of was convoluted, but my thesis was a combination of control theory and what is today called Hadamard models, which is actually beautiful. What is that? Generative models in NI. It's beautiful because you can prove something for that, and there are cool questions, and the study of those Hadamard models actually led to proofs of some combinatorial conjectures, which is kind of interesting stuff. But anyway, so when I came to America, what I really was good. So I was young, and of course I was smart, but I really knew very well linear algebra, and not because I had a good training in linear algebra, but because of control theory. Okay, and that was such a bliss. You do this control theory, linear about those things, and those little simple results, and people are happy. Okay, I just miss those blissful times. Okay. So and after that, it was quantum information. It was pretty much linear algebra, okay? Yes, it was pretty much linear algebra, okay? In my case, maybe I don't want to diminish. Yeah, I was also cute, so and in a way, again, I'm very happy for that my hyperbolic discovery, but it made my life kind of harder, okay? So now it's kind of bad when you become kind of serious about yourself. But it was such a bliss, all those little, and they kind of, many of them happen to be influential, so. Anyways, okay. Now we're going to, oops, how much time I have? No, but again, I will. Do I have like 15 minutes? It's to 4:40? 10 minutes. Huh? It's an hour. Okay. Yeah. So now the second result. So now what do you do in continuous time? In continuous time happen to be situations. So you can, in continuous time, you can have this kind of condition. So again, you will have a bunch of matrices. What do you want? You would like to essentially so what do you want? You fix a norm. You go through, this will be induced norm. You go through all exponents. And you want all those norms to be less than exponent to that gamma t, okay? And now you try to minimize this gamma over all possible norms, okay?
And now it's for each I.
Huh?
Now you're doing it for each
Yes, for each I, yes. Exactly. And for all positive t. Okay? And that is called, there are many definitions, but some people, I personally call it, it's a joint Lyapunov exponent. Okay? And again, the problem of so-called absolute stability is to check whether this guy, okay? And here's the problem. It's actually very difficult to discretize this question. It's very difficult to get, everything is finite dimensional. It's very difficult to get, okay? And there are two ways essentially to go from this problem to discrete problem. And they're both non-constructive. So one way is this, that this guy, what you want, So what do you want? You want to have some positive tau. Compute those matrices, identity minus. Not, you see, no exponents here. Okay? And you want joint spectrum radius of this thing to be less than 1. So anyway, so this thing is less than 0 if and only if there exists tau such that this thing is less than 1. Okay? Nobody, and again, there is no general algorithm to find out. This is one way to discretize. So again, I don't know tau, but I still deal, let's say, with finite set of matrices. But I can get to infinite set of matrices, compact. Okay, and here's what you do. You're considering those differential equations. Matrix differential equations. But what are those guys here? Those guys are Lebesgue measurable functions with this property that they are non-negative. And you fix, and you collect all solutions here, let's say at time moment 1. You run over this, and what I used here, they're Lebesgue measurable, they're non-negative, and sum of them is equal 1. So how you get to this guy? How you get to this guy? You're considering all possible, this is like this switching stuff. You're considering all possible switches. You at some on interval 0, 1. At some time you use one matrix, okay? After that you switch to another, okay? And you just keep going and you just feed all those switches on finite time intervals into interval 0, 1. It could be another interval, okay? And now, and you collect all those solutions which you get, all those product of exponentials, okay? But now you have no restriction on the switches could be an arbitrary small, and could be an arbitrary, and now you take closure, okay? You take all those, and you close this set. And it's happened to be that this is what you get, y. And here's the kind of funny situation that it's totally finite dimensional problem, seemingly. But you need those concepts. So essentially, what is happening, if you will take all those functions which are like this 0, 1s, 1, 0, 0, okay? And you take their, like this, and with that proper, again, you just take cases where those vectors are 0, those you use it's just Boolean, so one of them, okay? And what you take now, so you will have those functions, okay? And now what you take a weak limit in terms of L2. And weak limit will give you exactly those guys. And those of you who do quantum computing might recognize something here. So what is happening here? Here is interval 0, 2. And you do the switching. 1n, 0, 1n, and so you divide into n those guys, and you half 1, another 0, okay? And if you will have weak limit of those guys, it will be exactly function 1 over half. And it will be like this. And actually, this idea to use weak limits is actually very strong. It allows, for instance, to deal with this Lie formula when you have random choices of those guys. Okay. So, anyways, so here's the question. Okay. What is in discrete case if you have just two matrices? Okay. Moreover, you're promised that they're non-negative entry-wise, and they are L1 to L1 norms. Kind of absorbing Markov chains, kind of. Okay. And you ask in this case, you would like your decision question, is it to check whether this joint spectrum radius and P actually it's P-space complete. P-space hard. Okay? But it's certainly in P-hard, okay? The same will be true if you have this promise that it's non-expanding in respect to L2 norm, also will be hard. Okay. Now we go to continuous time case, and we have this promise. So it's just generalization of that, okay, but just exponents, okay? And I ask the same question. I would like to what is the complexity, and it could be any number of matrices, okay? So again, you know that those flows not contract in terms of L1. And again, it's like absorbing continuous time Markov chains in continuous time, okay? And you would like to check whether let's say all possible switches will kind of uniformly converge to zero. So what is your guess? Is this problem easy or hard? In discrete problem is hard. Okay, first of all, we do sanity check before I solve. I want to know this property, that each of them individually will converge to zero. Okay? So I will check whether spectra of each of those guys belongs in that left half plane. Okay? So I do this. This is sanity check. So it happens to be that under this assumption, each of them individually good, this joint system is good. There is no problem with switches. Okay? And way it goes back, okay? So there is a polynomial time algorithm, so we cannot have hardness result here. It's happened to be, I don't know how to, now we do the same question, let's say for L2 to L2. So which in this case would mean AI star plus AI. This what means that it's non-expanding in terms of L2, okay? So again, loosely speaking, it's an open quantum system. It can leak, okay? So now you have this question. You have this, let's say, open quantum system. Again, this is what I have. I have this non-expand, okay? And I would like to ask, is this complexity of this problem to check whether, okay? I don't know how to answer for 2. Okay? I don't know how to answer for 2. But if the number of them is n to some power alpha, and let's say number of them scales with n, the problem happened to be NP-hard. And that is the paper with that Alex Olshevsky, who is now associate professor at Boston University, okay? And that was in that IEEE automatic control. That was pretty kind of, okay, 2009. Well, okay. And so, and the thing is, there are really no good criterions for checking these things, okay? The only good things we can hope is, which is necessary condition, to check whether all possible convex combinations so this is natural necessary condition for that switching, that stability. That all their convex combinations are good, meaning the spectra is that in left half plane, okay? Necessary, but it happened to be not sufficient. And there are many cool examples. And there are many questions about that. But it's happened to be, so what is that idea of hardness proof? And again, a proof is uses measure theory. So you need to look for a gadget such that this is, first of all, with this property. Such that, on one hand, this condition is sufficient for that thing. On the other hand, to check whether those guys are, Gurvits, actually, it's the same name as mine, is NP-hard, okay? And the structure which works is the following. So the matrices of this structure, 0. So you see it's a real case, okay? Here -1, okay? And this question about the Hurwitz stability of convex hull, it boils down to this question, to check whether this matrix, for those guys, is just non-singular. So this is the question. Given bunch of matrices, to check whether all convex combination of them are non-singular. It's the problem, which is like very famous, is to check whether all convex combination are singular, and it's known to be that polynomial identity. Okay, here's okay, but this problem happened to be NP-hard. Okay, and the reduction is using. The reduction is using the maximal independent set. But the funny thing is, there are many ways. In the original paper, I had this very torturous way to get from maximal independent set for that Motzkin theorem to this matrix formulation. But eventually I realized, my God, it's so simple. Why? So again, roughly it will be this question. So it will be this adjacency matrix. And it will be some constant, which comes from Motzkin theorem, and this polynomial. And you would like to express this polynomial as a small size, as a for some small size matrices. So if that G was n by n, that must be n square or something like that. And I had the construction. But I thought, my God, it was so stupid with some perturbations. This is standard result about determinantal representation of polynomial with small arithmetic complexity. So here it's a quadratic form that, it's valiant stuff. Again, it's maybe not constructive, actually you can do it. I had a constructive way, it was kind of messy. But Valiant gives you this representation. Okay? But if those guys are probabilities, that it can be written as that's it. And now on this, but again, the main thing in the proof was to prove that for this structure, this spectral condition is equivalent to that thing, which is in general not true. Okay, and it's still open question as far as I know whether under this condition that non-expanding in L2, that spectrum condition is sufficient for that absolute switching stability. It's not, but in this case, happened to be true. And again, and proof goes through uses Lebesgue integral. Some simple but measure theoretic things. Otherwise, you know, it's So this is it. And again, let me finish to explain why another reason why I decided to talk about this thing. So I did this stuff a while ago and then explained. But my impression now, when I read some literature, people still cite, you know, people probably don't connect that person who wrote those papers and the person who did this operator scaling and hyperbolic polynomial. I think they're probably two different people. And why I think so? Because you know that in People's Republic of China, this is like big thing. They write those millions of papers with minuscule improvements. But moreover, most of the time, minuscule improvement is just rewriting of it. For instance, many of my quantum papers, they just change the definition, and you know, like paper about the separable ball, they just change the definitions, the same stuff, okay? And of course, nobody has time to go through all the things. So I want, you know, people, especially now it's kind of televised, I want people, it's the same person who did that stuff and, you know, hyperbolic stuff, okay? This stuff unlikely will make to the book of proofs. Unlikely. But still, you know, it's my legitimate kids, you know, I don't deny them. Yeah.
Okay, Leonid, thank you very much. Any questions, quick questions, I guess? We're a little over time.
So guys, if you're interested in that references, send me a mail. And again, most of the stuff I talked here is published. On the other hand, these days, the most valuable stuff is not published stuff. Because ChatGPT does not know about that. It belongs only, if it was something to belong only to you, don't publish. No, I'm just kidding.
Okay, well, maybe we'll just hold questions till after the time. Anyway, let's thank Leonid again.